now to add some comments on shears, a special type of mappings which are useful in graphics. So just take it as an illustration. And what I mean by shear, so shear is a map which is of the form 1, 1, 0 and A. So that's the matrix. So if you just hit a general vector, so what you get is x plus A times y, and here y is copied. So if I imagine that I would be just mapping the plane into plane by that, then here I've got some say coordinate grid like this. And what will happen is the horizontal ones remain as they are, that's the copied y, but the vertical ones get much more shifted, right? So the origin goes to origin. So you see everything is sort of sheared. And the point is that this kind of mapping is very useful because it's very easy to manage in graphics, right? So if you imagine a screen full of pixels, you just push the pixels in each row a bit to one side, and how much to push them is given by how far you are from the zeros one. And that's exactly it. So it's very fast. Whereas if you want to do rotation, so it's completely different, right? So there is a lot of computational power necessary because you have to recompute the cosines and sines and get everything sort of shifted, right? For each pixel separately. So it's much slower. So how does this work? So I follow the text in our textbook, and there is something preparated there. So if you go here, so there are the shears. So I go to the Sage cell, and right, so that's where we are. So you see that what I want to show is that actually you can use the Sage also to solve theoretical problems like we shall do here, right? And what I will do is I will first block the lines, so just to imitate that I would be writing them one by one, always following what I've got already, including the final one. So now if I do what's there, so you see what I do, I introduce three shear matrices. One is the horizontal one, the other one is a vertical version of the same thing, the third one is again horizontal. It doesn't make to compose two horizontal ones in a row because it's again a horizontal one. So what you get is just I hope it works, yes, you get the matrix of the composition of the three shears. And you see that if we want to get it as a rotation, so rotations are of this kind, so it's just this, and you have got the cosine phi, and here you have got sine phi and minus sine phi, and no, how is it? Cosine, no, plus sine, minus sine, cosine phi, right, this way. That's the positive rotation by phi. So you see that I've got the same thing here and the same thing here, and I've got here the two up to a sine, right, which can be different. So if I go back to what I got, so you see that in order to get the same thing here and the same thing here, B must be equal to C. So that's the necessary condition. So I can improve it. So I just, in my matrix, I just substitute B equals C, and he will show it to me because I didn't ask him to show me the result. So now you see, so we are getting something easier. And now the remaining equations are that so what we want to see is that in order to have rotation, so the square of the elements in the first column summed together must give 1. So it's this one, so x 0, 0. Remember, Sage counts everything from 0 square plus x1 0 square minus 1 should be 0. So that's the first equation which I add. The second equation is that the bottom one must be the same as the upper right one. So that's the x1 up to sign. So the x1 0 should be minus x0 1. So that's the second equation. And the third equation is already fulfilled, right? Because we just guessed this. So that's okay. And now we ask the Sage to solve it. And to print us the solution. So you see he's struggling a little bit and now, but he gives us 3 solutions. And you see that the solutions say that they've got 2 parameters, R1 and R2, which are free parameters for the solution. That's expected if it should be a rotation, right? So why not? Because we had 2 free things left there. And it says that B is actually the sign of the rotation. Right? So R1 is the free parameter and it computes what the A and B must be. Right, and then what I prepared also as where was it? Here, yes. I also prepared a illustration, graphical illustration how this really works. How to imagine that the shears now again, just let's have a look a little bit what the code is doing. So I just import some graphics things and I just define the shear transformations, right? So in coordinates x and y, and the shear factor is just the A, which we had there, or B or C. And this is the vertical transformation. So here I add it just rather to y than to x. And now again, as earlier, I use the interactive mode and define what should be happening, and I move with the sign of the angle of rotation, and I move it by 2%, by 0.02. So and I want to show somehow how the shears are making the rotation. So this is just drawing some object. So that's nothing very interesting. So this is the object, and then I make the shears of the things, and finally I show everything, right? So if we evaluate it, I hope it will work, and you see this corresponds to no rotation at all. And if I move the B a little bit, then what happens is that you see that first I'm doing the horizontal shear, just pushing everything to the left, and so everything is squeezed to the left, but the epsilon values stay as they are. So the further I am, the further I am squeezing it. Yeah, it's a linear transformation, so it keeps lines, so it maps lines to lines. So if I map the points, I can automatically map the segments, right? That's right. Then I make the vertical shear, and then I do the same shear as before, because that's what the Sage told us in the solution. I didn't point it out, but it told us that actually you can get each rotation by getting the right shear, another vertical one, and then the same one as the first one in the same direction, right? So that's what's happening. And you see, if I increase it, then it will be the same thing, except it's more visible, right? So this one goes further, the vertical one is not much different than before, and then I go here, right? So that's the presentation I wanted to show, and then please just play with any other transformations and look how they are working, because the matrix calculus is a very nice tool to do nearly everything. So that's it.